Hi everyone, my name is Andrew Mo, and today I'll be going over the results of my Physics 2212 Lab 4. And so the purpose of this lab is to basically predict the behavior of parallel and series circuits containing resistors and measure conventional current and potential differences in the circuits, as well as to learn more about components of RC circuits and measure properties of them. The goal of this lab is to basically learn about parallel and series circuits, RC circuits, and basic elements of circuits such as resistors and capacitors. The results of this lab is that we successfully predicted the behavior of parallel and series circuits, as well as we found the time constant of the RC circuit to be 6.04 seconds. And so there are basically two fundamental principles that are applicable to this lab. The first is the conservation of energy, which states that energy can neither be created nor destroyed. And this helps us derive loop rule, which we're using later in this lab. And the next is current conservation, which is an extension of charge conservation, which basically states that charge can neither be created nor destroyed. And this helps us derive node rule, which we'll also be using later in this lab. And so we're first tasked to basically predict the values of I1 and I2 in the following series circuit. And using Ohm's law, loop rule, and node rule, we found that I1 and I2 were both equal to 0.024 or 0.0204 amps. And after creating the simulated circuit in the Colorado Effect circuit construction kit, we found that our predictions were correct. And it's also worth noting that if one of the connections to the ammeters was reversed, the ammeter will read a negative value. And so after replacing an ammeter with a voltmeter, we found that the other ammeter's value is 0 because the circuit is not closed and therefore has no current. The voltmeter itself reads 3 volts because of the potential difference between the 2 points that the voltmeter touches is 3 volts. And so now we close back the circuit and we're measuring the voltages at each point in the circuit. And we found that for segment AB, it was 3 volts. For BC, it was 0 volts. For CD, it was negative 0.96 volts. For DE, it was 0 volts. For EF, it was negative 2.04 volts. For FG, it was 0 volts. For GH, it was 0 volts. And for HA, it was also 0 volts. And so summing up all the voltages across each segment of the circuit, we found that the total electrical potential difference across the entire circuit is equal to 0. And that's pretty much expected with loop rule. And with these segment results, we graphed the potential difference across the circuit and obtained the following graph. And it's also worth noting that the ammeter's reading does not change if we were to put the voltmeter on the segments of the graph on the circuit, because the voltmeter has such an a high internal resistance and basically diverts no current from the circuit. And so basically now we added a ammeter that's parallel to the 100 ohm resistor, and the ammeter itself has very little resistance, and it's much less than the 100 ohm resistor. And so the current chooses a different path of least resistance, which is basically the one with the ammeter, and basically the current increases and flows into the other ammeter. And we also calculated the resistance given Ohm's law. We found that the resistance for the 47 ohm resistor is 47.95. For the 101, it's 102.05. For the wire and for the ammeter, it's 0, just because the change in potential difference is equal to 0. And so now moving on to the RC circuit analysis section, we basically created this initial circuit, and we observed that the light seems to be bright initially and slowly dims as time passes. And the current also starts off normal and then starts to slowly slow down as time passes. And after removing the circuit and connecting the light to the capacitor, we note that the light again starts brightly and then slowly dims as time passes. And the current also starts off normally and then slowly slows down as time passes. And after measuring the time, using the 10 ohm light bulb, we found that it dimmed after 19.9 seconds, and with a 20 ohm light bulb, it dimmed after 39.8 seconds. And so now we graph the voltage, the voltage for the 30 ohm light bulb at each second for 20 seconds. And we obtained the following data results. And after plotting the the natural log of the voltage with the initial voltage, we got the following graph with this line of best fit equation. And the expected time constant was supposed to be 6 seconds. And using the actual time constant formula, which is -1 over the slope, we got an actual time constant of 6.04 seconds, which is not too far off of our expected one. And so there are basically two assumptions to this circuit. The first to this lab, the first is that the circuit construction created by the Colorado Effect works as intended, and that the circuit builds match the provided circuits. And there's basically two errors that could have arisen from this lab. The first is human error in recording the data during the RC sections, and if the assumptions are true, then there should be no other errors. And so for the first questions of the what if, I answered that if I use an actual ammeter instead of an ideal one, I believe that it would get lower current values for the parallel and series sections. Since real life ammeters does not have 0 resistance, current will be lowered by Ohm's law. Therefore, the current values shown in the ammeter would naturally be lower. And for the second what if question, theoretically, if there was no resistor in the circuit, the capacitor should charge immediately and take no time to reach full charge. However, this prediction would not happen in real life since there are many parts of the circuit that will inherently have resistance due to human manufacturing errors.